Yes. Fine. Are you good? Are you done? Oh, good, thank you. I was supposed to drive my friend to the airport.
Oh.
He showed up at my house and then 7 o'clock, he called me and like, oh my God, I gotta take you here. But I did not go to sleep at a time last night that was conducive to taking your friend to the airport at 7 o'clock.
Where?
Ontario.
Okay.
I live pretty close to Ontario, so.
Okay.
Yeah, I was trying to get it done by today, but things come up yesterday, so. I'll get it done. Tuesday, we'll talk about it for. It's not due Tuesday, so we'll talk about it Tuesday. I pushed the due date back over the weekend. So sort of about. That chair is kind of cursed because the legs are so thin.
Yeah, okay.
That part actually. X activity, challenge even.
So excited.
All right, it's 5:30. Let's go and get started. Right, good evening, everyone. How's everyone doing today? Okay, well, better than not okay. Yes. Okay, so I know I made a very grand promise to you guys on Tuesday that we talk about the midterm project today. Still don't have it done. I'm sorry about that. So, but Tuesday for sure, it's top of my priority list for tomorrow and Monday too. So Tuesday we are going to talk about it. I did push the due date back, and so I know some of you guys will be taking the comp exam or when it was originally due, end of March. But I did push it back just, for those of you who are taking the comp exam, to have kind of an extra week to kind of put them. Because I know that last, week or two before the comp exam, you'll be studying furiously. So I did push it back, and so, this actually kind of aligns with kind of the original timeline of about, 5 weeks to do it. Okay. Okay, so we'll talk about that on Tuesday. I did do some work on it, but it's just not quite ready for. All right, so today we're gonna have a full lecture then, and so just like kind of mentioned at the end of class last time, we're gonna start today talking about the idea of a mesh convergence test, and so we'll talk about what that means and kind of what that means in the context of all the element stuff that we've been going over. And then we'll start to introduce some special elements. So next Thursday, we'll be doing activity 4. And activity 4 is all about how we use these special elements known as shell and beam elements. So we'll introduce those, kind of define what they represent, what they're all about, and kind of what kind of advantages they may have over the traditional solid element. Kind of okay. All right, any questions I can answer before we get started for today? Okay, good. All right, so let's go ahead and get started. So we're going to start today with the discussion of the mesh convergence test. Okay. So we spent the last couple of weeks, talking all about the different elements, right? Going over the pros and cons of the different shapes, tetrahedrons, hexahedrons, triangles, quadrilaterals, looking at differences in their shape functions, as well as the linear and quadratic. All that is really good. But ultimately, all of these, all of this kind of background information, all of these discussions ultimately lead to, what is the best kind of mesh? What is the best, mesh that we can use to get the best results? So remember, we kind of defined what a good mesh was kind of earlier this semester. So ultimately, a good mesh is one that's going to produce accurate finite element results with the least amount of computational cost. And so basically, you want to refine your elements enough, you want to use enough, just enough element order in order for your results to be accurate and reliable. Okay? You can go more than this, of course, but then, you use excess elements and you're kind of just, taking up extra resources, which, in the finite element world is usually not the end of the world, but, you want to reduce that if you. Okay. So let's kind of remind ourselves briefly of all the levers that we have to turn, or all the kind of different ways that we can tune our mesh to get these accurate results. Okay. Okay. So most of the ways that we can tune our mesh have to do with changing our element settings, right? So the element shape, order. So we spent a great deal of time talking about those two factors and how those affect our results. Okay. But most importantly is the element size. But all three of these factors kind of contribute to how accurate your results are going to be and how costly or how time consuming the simulation is going to take. All right, so now, now we can kind of finally start to ask the question of, how much cost is enough? How many elements are enough? How do we know, right? We've discussed all these different factors and kind of, intuitively or qualitatively, I've kind of, discussed with you guys how to tell if a mesh is good or if a mesh is not good, right? Now we can finally start to get into, how we can actually define this and how we can actually prove it to be true. Okay, so what is a mesh conversion test? A mesh conversion test is basically the tool that allows us to kind of prove or justify our mesh is good enough. So a mesh convergence test is a tool which ultimately what's going to show is going to show the convergence of a particular finite element result. We'll talk about what convergence means in a second, but it's going to show how a particular finite element result converges as the size of the element changes, or another way to say it, as the number of as the number of elements in the mesh increases. And so, just kind of based on the definition there, a mesh convergence test is mostly focused on element size, but the other factors like the shape and the order and other stuff are going to play a role into it as well. Okay. But it's important to note that, mostly mesh convergence tests focused on the size of the element. Okay, so to kind of show you a mesh convergence test, I think the easiest way is just to kind of show you what it typically is. Mesh convergence test, the way it's typically shown is it's shown as a line graph. So usually what you're going to see is a graph that looks like this. So this is something that's almost always presented in a lot of finite element studies. Maybe not the graph, but usually it's mentioned somewhere in the finite element study that the mesh convergence test was performed. Okay. So on the horizontal axis of this graph, typically what's shown is typically the number of elements in the mesh. And then on the vertical axis, you have some result that you're stress, the strain, or the deformation, something like that. I'm gonna say, the vertical axis is some result of it. Okay. Okay. So typically for a mesh convergence test, in order to run it, in order to kind of show this, you need to run multiple simulations on the same object with the same boundary conditions. Okay? So the data points on the mesh convergence test are produced by running the same simulation, but successively refining the mesh. Okay. So basically, each data point that you're going to see on that graph is going to be a separate simulation. Okay. So the way to do this is you're going to take your simulation, or you're going to take your FEA. You're going to run the simulation with a fairly coarse mesh. So you're going to run it with a mesh size that's fairly large, and you're going to observe, what the value of a certain quantity of interest is going to be. So some common results of interest would be maybe the maximum deformation in the simulation, maybe the maximum stress. Okay, and you're going to plot this yourself. So I believe in ANSYS there's actually a way to automate this, and so you can have ANSYS run a mesh convergence test for you. But I've always just run these kind of manually, just because it's for me it's a good exercise in seeing the mesh. Okay. Okay, so let's start. So let's say that you ran a particular simulation, and you obtained a data point right there. So let's say this data point, this is your start. You can see here, because it's on the left side of the graph, you can see it's a fairly coarse mesh. And so maybe it only has a few hundred elements or something like that, right? So that'll be kind of our first data. And just for the sake of this example, let's say that from the simulation, we measured what the maximum deformation was. All right, so we ran the simulation, we observed what the max deformation was, and we plotted it in our. Okay. Now, let's say that we ran the same simulation. So we kept all the boundary conditions the same, all the material properties the same, all that good stuff. The only thing we did was we refined the mesh a little bit. So we changed the mesh size to be slightly smaller than. Okay, so by making the mesh size smaller, we're gonna increase the number of elements. Right, and so by increasing the number of elements, we're going to progress to the right in the horizontal axis. Okay, and what you should see is that the value of your quantity of interest is likely going to change if you started with a coarse enough mesh. Okay, and so you can measure kind of the max deformation again, and you may see that it increased, maybe decreased based on the size of your mesh. Okay, and that gives us our second data. All right, so you can continue this, and so you can continue this, kind of keep running simulations, keep successfully kind of refining the element. Your data points might look something like this. So I'm drawing you kind of an idealized version of this. A lot of times your mesh convergence test is not going to be this smooth, but it's a good, it's a good way to kind of show what the trend should look like. Because eventually, if you refine the mesh enough, the results are actually going to stop changing. So eventually, the plot is going to flatline. If you refine the mesh further, you're not going to obtain any further improvement on the solution. Connect all these points together. You can start to see a trend in your results. So ideally, you're going to reach a point where if you refine the mesh further, you're not going to see any improvement or any change in the solution. All right. And so once you kind of reach that point, once you kind of reach a point in your mesh convergence test where your plot is starting to flatline, then at that point we say that your mesh is converged. Results have converged. Okay, so for this plot right here, maybe I would pick this point right here. So this right here is what we call the convergence. And so what this is telling us is that further refinement of the mesh is actually not going to lead to any improvement on the solution. And so, you can keep refining, as long as someone else is paying for the electricity, I guess. But it's not going to lead to any kind of. And so this plot, what it shows is, so, let's say that, you're writing a finite element report, you're doing a midterm project or final project, or something like that. And you report that, I have used a certain number of elements. So let's say that this point right here is a 25,000 elements. You may write that in your report, and then the first question that everyone asks is, why did you use 25,000? How did you come up with that number? Well, and then you can show your mesh convergence plot and say that, with 25,000 elements and the element shape and the element order that I've chosen, my results have converged. No point. This graph shows that there's no point in kind of, going any further. Okay, any questions on this? Okay, good. All right, so what is happening here? So why are we seeing a change kind of in the first kind of portion of this graph? What is happening over on this? Okay. So when your mesh is coarse, there's a phenomenon that occurs called numerical error. So numerical errors are nothing more than just, the computer is trying to approximate the solution to your equation. It knows what the equation is, but there just aren't enough elements, or there's just not enough resources available to them to compute an accurate solution. Right? And so coarse meshes are very prone to these numerical errors, just because there's not enough elements, not enough resolution to produce an accurate solution. So the good thing about numerical errors is that they are kind of the easiest errors to kind of deal with. And so the best way to deal with numerical errors is to, provide more resources, either, in this case, providing more elements, and so refining the element size. But you can also do things like, maybe improve the element order, maybe choose a different shape, things like that. And so the number one thing that you have to make sure when your finite element study, you're choosing number of elements, you want to make sure you minimize these numerical errors as much as possible. Okay? It's impossible to get rid of all numerical errors because, you know, just by the nature of using a numerical technique like best FEA, there's going to be numerical errors, but, you know, you want to do everything you can to minimize that. And that convergence test kind of shows that you've done it. Okay. Any questions on this so far? Good. All right. So your mesh convergence test is an essential part to, you know, almost any finite element study. This would be good to include in all of your activities up until now, even though I may not require it for everyone. This is going to be a requirement for the projects, so midterm project, final project should have a mesh convergence test, right? Now it's important to note that certain quantities or certain results from your FEA may be more difficult to converge than others. And so sometimes if your mesh convergence test, if you form the mesh convergence test on a result that's typically easy to converge, you know, it may give you kind of a false sense of security in terms of the other. So, you know, there's no equations for this. There's no kind of hard or fast kind of rules to this, but, you know, I can give you at least some rules of thumb, so that when you do choose your mesh convergence test, you kind of make sure you choose a kind of thought based on what you're trying to do. Okay. So rule number one. So rule number one, generally speaking, average results, or in other words, results that are averaged across the entire model are easier to converge than maximum results. Right, so average results, you know, typically you're going to be averaging a certain result, maybe the deformation or maybe the stress in a particular region, or maybe you're averaging across the entire simulation. And so because of that averaging process, you know, a lot of these kind of small numerical difficulties are all averaged and kind of smooth over in that process. Whereas if you look at maximum results, the maximum always usually only occurs at one particular location in your model. And so it's a lot more sensitive to, you know, the mesh density in that particular. So, you know, if you show converged results for like average stress, you know, you may not be converged in maximum stress, but that also might be okay in some situations too. And so, you know, I'm not giving you these guidelines to say that you should do the most difficult convergence. Because a lot of times it's going to depend on what exactly you're trying to get out of the simulation to begin with. Okay, rule number two. Rule number two is that primary solution variables are easier to derive or easier to converge than derived ones. So again, primary results are kind of the first things that are solved from an FEA simulation. So things like deformation. These are always going to be easier to converge than derived results like stress. We're going to dive a bit deeper into this, probably more on Tuesday. When we talk about shell and beam elements, but derived quantities can be very difficult. Okay, so those are kind of the two main things. So when you're choosing what to display in your mesh convergence test, kind of keep these things in mind. But again, you don't have to choose the most difficult convergence test all the time. So I think in the past, I've typically told people to try to get convergence on maximum stress, because maximum stress is kind of the more difficult side of both of these. But again, maybe maximum stress is not something that's important in your simulation. Choosing a convergence, when choosing a convergence criteria, think about the objective, or think about what you're trying to get out of the finite element simulation, and then go based on that. But ask yourselves questions, are you actually trying to simulate the max stress accurately? Right? Sometimes yes, sometimes you do want to find out what that max stress is, and you want to make sure that your simulation computes that accurately. So it makes sense to choose that as a convergence criteria. But maybe it's not. Maybe you're just interested in the deformations, and so in those cases, maybe you converge a lot sooner. Okay? You can also run multiple mesh convergence tests as well, so you're not limited to just one mesh convergence test at all. So if there are multiple things that you want to show convergence of, you can definitely show multiple convergence tests as well. Okay. It's all about kind of how much you want to say and how much space is going to take up in your. Last semester I had some transfer students from Germany, actually, bless their heart. But when I introduced this idea of the mesh convergence test, they thought I wanted to see a convergence test for every single quantity and every single configuration of their mesh. And so their midterm project, their project report was ended up being like 90 pages long, but 70 pages was just line graphs after line graphs after line graphs. So I was like, all right, guys, that's a little bit overkill. I don't need to see 70 line graphs. And so, somewhere in between 0 and 70 is kind of a sweet spot for the number. Probably closer to 0, but not exactly 0, but closer to. All right. Any questions on this? Okay. Oh, questions. Question in the chat. So, Professor, are you saying that convergence of element numbers may differ when comparing normal stress, equivalent stress, and deformation? It will, yes. And so, normal stress and equivalent stress, probably the convergence of those are similar because they're both stress-based quantities, but they are going to be different than deformation as well. And so when you're choosing your convergence criteria or what you're going to use to assess convergence, you want to be kind of thoughtful in terms of what you select to be that. Yeah, because the convergence for deformation is going to look very different than a convergence. Okay. Good. All right. So how does this relate? So, the mesh convergence test is a great tool. And so you definitely should, present one. But again, it's mostly focused on just size. So how do things like element shape and element order, how does that factor into mesh convergence test? Because those are going to affect the convergence as well. So because we've already discussed that those things affect the accuracy of your finite element simulation. And so, we've mostly just been discussing one axis of mesh change, which is just the element size, but really there are multiple axes. So, how are you going to factor in those element orders and shapes? Well, the way that is typically displayed in practice is that you typically show multiple mesh convergence tests for different meshing techniques. So if you want to make a comparison between linear elements and quadratic elements for your finite element mesh, usually you're going to show the mesh convergence studies for both of those on the same plot. And usually what should happen is that your quadratic element should converge faster than your linear. So for example, let's say that we did a mesh convergence test. So down here will be number of elements. On the vertical axis, let's say that we're going to be converging on average stress. Let's say that you ran the simulation with linear elements. So with linear elements, maybe your convergence plot looks something maybe like. So you do reach convergence, and so you can see that we've converged. But maybe you do so with a high number of elements or a fairly small mesh size. Okay. If we do the same test, and so we kept the boundary conditions the same, everything else, but we reran it with quadratic elements, your convergence plot may look something like this. And so here, we've used the mesh convergence plot to show kind of a comparison between linear and quadratic. And this is typically what you should see, is that with quadratic elements, you should converge faster. So in other words, you can get numerically accurate results, or in other words, you can minimize numerical errors with less number of quadratic elements than you can with linear elements. Okay, and that tracks, and so that's generally what we expect. But we also know, just based on our discussions kind of over the past week, that on a per element basis, the computational cost is greater. So just kind of keep that in mind. It's hard to exactly quantify exactly how much more expensive quadratic elements are compared to or added mid nodes or added things like that. But you can expect an increase in cost. Now, this may kind of beg the question, ultimately, with these mesh convergence plots, we're using, the number of elements as kind of a surrogate measure for cost, right? And so ideally, instead of number of elements, what we should be doing here is computational cost, right? Because ultimately that's what we're going to pay. And so, if who really cares about the number of elements if it's, when it's time and money and resources that we're using to run the simulations. And I agree, right? And so, ideally, these mesh convergence plots should be based on cost rather than just number of elements, where number of elements is just kind of one indicator of cost. It's just that computational cost is a very complex thing. It depends on the computer you're running the simulation on, how many processors you're using, whether there's like some weird dust going on in your computer, something like that. So cost can sometimes vary, from simulation to simulation. It certainly varies from computer to computer. So kind of the most consistent thing that we can measure is the number of. Okay. So that's kind of generally how, and you can make similar plots like this comparing different element shapes. And so you'll often see that hexahedron will have kind of the same behavior as quadratic elements. They'll converge faster than triangular elements or tetrahedral elements. So that's typically how these are kind of compared. All right, any questions on this? Yeah.
Instead of saying number of elements, we said number of nodes. That's something we can quantify.
Yeah, yeah. So number of nodes, you can do that as well. So you can definitely do the mesh convergence test with number of nodes as well. It's just that traditionally, in most sites they use number of. I'm actually not sure why. I would agree with you that number of nodes is probably more correct indicator for cost because that determines the size of your. So you can absolutely do this with number of nodes too. I think you'll get very similar behavior. But yeah, I'm not sure why elements is kind of the standard, but yeah, but node you can absolutely do with nodes. Okay, good. Actually, speaking of that, another way that you might see these mesh convergence tests, instead of number of elements, you may see them displayed as the element size. But I don't particularly like this form of the mesh convergence plot because you kind of have to read it backwards. Because generally mathematically in all other math classes, when you see convergence, it usually goes to the right. But with element size, you're gonna have to look at it in reverse because you're converging as the element size gets smaller. And so usually looks kind of something like this. Even weird for me to draw with my right hand. And so with kind of the opposite, with element size, you're going to get convergence to the left, okay? Which there's nothing wrong with it. And so, it shows you the exact same information. It's just that for me, it's kind of weird to read it right. Certain people, certain papers will prefer this. And so if you're looking in the literature, you're looking at finite element studies and the mesh convergence plot backwards, look and see what's on the horizontal line. Oftentimes they'll do that element size. Yeah. But personally, I prefer this way. But if you guys are in your reports and projects, if you do it this way, I'm not going to mark you down. I have my preference, but this is equally as valid. So do whatever kind of feels more comfortable with. I think people like this one because the element size is something that you directly input. And so when you were specifying your mesh, the element size is what you directly kind of put into ANSYS itself. You don't really have direct control over the number of elements. That just kind of results based on the size of the elements that you do. And so element size is kind of a more direct kind of I put this size and then this is the result that I. Anyway, that's what I think is the logic. Okay, all right. So that's mesh convergence tests, and so very important parts to specifying your mesh settings, and kind of a core thing that we're going to do. All right. So for the rest of class today, we're going to start to talk about some of the more specialized features within ANSYS. Features and things that you may not use in every single simulation, but can be actually very useful in certain situations, right? And so kind of keeping on this theme of meshing and elements. And so we're going to talk about first some specialized element types called shell and beam. So in a nutshell, shell and beam elements are specialized element types within ANSYS that you can use for certain situations for more accurate. We're going to talk about the situations where you would want to use these shell and beam elements, as well as their benefits. Well, the main benefit is that for these situations, for the situations where shell and beam elements can be used, they often lead to much better convergence of the solution. You're going to have much faster convergence with a smaller number of elements using these special element types in near convergence situations. Okay, so what are the situations where you would want to use shell and beam elements? So you want to use these elements when your geometry exhibits certain features or certain types of in particular, shell and beam elements excel in meshing geometries that are thin or slender. That's kind of the qualitative kind of definition for that, but kind of the more kind of exact definition is when you have a geometry where one of the dimensions, at least one of the dimensions, is much smaller than the other ones, that's usually a good indication that you want to use shell or beam. Okay, let me give you a couple examples. So, kind of the most quintessential example for shell elements are going to be, very thin plate-like geometries. Geometry that may look something like this. Very long in 2 dimensions, but very small in one of the other. Should not be touched. The plate's supposed to have a uniform thickness, just ignore my poor drawings. Okay. Okay, so in this case, this dimension here, the height of the plate is much smaller than the length and the width of the plate. So this would be a great chance to use shell elements. All right. quintessential kind of situation to use a beam element as well for a beam-like geometry. Let's say that you have a geometry, with a square cross section, very, very long like this. That would be kind of the perfect opportunity or the perfect chance to replace this with a beam. Okay, so if you notice from these two examples here, these are objects that, are technically three-dimensional, right? They should be three-dimensional, despite how I drew them. But for most cases, if you were to analyze this in practice, you would consider them either a 2D or 1D scenario, right? So this thin plate right here, this is essentially a 2D. Where this slender beam here, this is essentially a 1D scenario. Right? At least intuitively, we think of it in that way. And so if that's the case, then it should, it makes sense to use elements that kind of match up with the geometry. So instead of using a fully three-dimensional element, we should use two-dimensional elements for thin plates. Instead of fully three-dimensional hexahedrons, tetrahedrons for a slender beam, what if we replace it with one-dimensional elements? Okay, that's going to save us a lot of cost, and it's going to save us a lot of kind of headaches with conversion. That's exactly kind of the motivation. So shell elements are kind of specialized 2D elements. They're not quite the same as 2D elements, so they're actually different than the 2D elements we use in activity 1. We'll talk about kind of the differences there. And beam elements are essentially modified 1D elements. Kind of the benefits of this is that for shell elements, like you've seen, 2D elements have much less nodes. They have much less hit functions too, and so they're on a cost wise, they're much more efficient. And 1D elements are even cheaper than that. So 1D elements usually only have 2 or 3 nodes to them. Which is okay. Any questions on this so far? Okay. So what are the benefits of using these types of elements? Well, I think maybe a better way to phrase that is that the benefit of these special elements is that they avoid the difficulties and challenges of using 3D elements to mesh these geometries. And the reason 3D elements kind of struggle in these situations, I've kind of discussed this with some of you kind of individually as we work on the activities, is that generally speaking, if you're going to be using three-dimensional elements for any geometry, typically you want to have multiple elements through the thickness, right? And so there's kind of a rule of thumb in finite elements where you should not have any region of your model where it's just one element thick. So, this kind of came up when we were talking about, mostly activity two. As I was kind of going around and help and kind of, talking about the meshes, with you guys. Right, some of you, if your mesh was a little bit too coarse in activity two, then you ended up with the situation where your entire bike crank, or the entire width of the bike crank was just one element. For example, so let's say that we had kind of a beam-like geometry. I was gonna draw the bike crank, but I didn't want to. It's gonna take longer for me to try to draw it than to make a point. Okay. So let's say that we mesh it in the following way. So let's say that we apply a mesh and it looks something like this. In other words, the mesh nodes are kind of looking like the following. All right, so this would be a situation where we only have one element through the thickness. So if we were to kind of travel, so let's say that we travel from the top of this structure to the bottom, we can travel that distance there. So we can travel from point A to point B. So as we travel from point A to point B, we only cross through one element. So that's what I mean when your geometry or your mesh is only one element thick. Okay. Now this is the reason this is kind of challenging here is that there's no interior nodes, and so all the nodes for these meshes are existing on the boundaries of that geometry. And for these types of geometries and just for finite elements in general, you always want to have a healthy amount of interior nodes when you are computing your solution. And when your geometry is just one element thick, then you virtually have no interior nodes. Okay, the reason you want to have interior nodes is that a lot of your quantities are computed based on derivatives, right? And I'm not just talking about the stresses and strains of your results, but even in solving the differential equations, the governing equations of the FEA, you're going to have to take derivatives of quantities at some point as well. If you only have exterior nodes in your simulation, then you're basically not getting any kind of information from the interior of your geometry. And a lot of times, especially for structural simulations, you need that information from the interior in order to correctly compute things like deformations and stress. And so if you're gonna be meshing these geometries with solid elements or hexahedrons or tetrahedrons, you want to make sure that there is at least from the outside. It's very hard to look at your mesh from the inside. I do it, but at least from the outside, there should be some indication that you do have some interior nodes in the geometry if you want to have an accurate result. Okay. Another reason why interior nodes are important is because interior nodes are not acted upon directly by the boundary conditions. So every single exterior node in a finite element simulation has some boundary condition applied to it. Now, granted, most of these boundary conditions are going to be the zero stress boundary conditions that we talked about before. Those have a very minimal or very negligible effect on the solution. But there are a lot of exterior nodes where you have forces applied, you have maybe constraints applied, and so those are going to strongly affect their solution and behavior as well. And you don't want those boundary conditions to be the sole determinant of things like the stress and deformation in those areas. Okay, so having interior nodes kind of hedges against these things where you have accurate behavior that's not just directly specified by the boundary conditions. Because if you don't have enough interior nodes, you kind of run the risk of your result being like directly, what I say, kind of directly specified. So you're directly specifying what the solution is, and you're not letting it come about naturally as from solving these. Okay. Okay. There's other reasons too, especially in other domains too, like fluid mechanics especially. You want to have interior nodes. Without interior nodes, you are not going to cut out solution at all because everything is just going to be a no slip boundary condition. But there's other reasons, but I'd say these are kind of the most important. All right, any questions on this so far? Okay. So when you have a thin or slender geometry, it can often be a struggle to get interior nodes using solid elements without kind of exponentially raising the cost. Okay. Oh, I should define. I've been saying this the whole time. So when I say solid elements are kind of our traditional kind of elements that we've talked about before. So solid elements are things like tetrahedrons or hexahedrons. So these are our 3D elements. I apologize. I've been using that term all day today, and I haven't really properly defined. So the challenge with using solid elements in these thin and slender geometries is that you often need to put an inordinate amount of elements in order to get a proper amount of interior. And oftentimes, you end up with the mesh, for just a very simple plate, you may get a mesh that is, 2-3 million elements, which kind of seems like overkill for some. So the challenge is that, when you specify a mesh size for solid elements, that mesh size is applied for every edge of that element itself, right? It's very hard to kind of intentionally create skewed elements. Let me show you an example with hexahedrons. Okay, so let's say that we have a very thin plate. I'm going to blow it up for a second just to kind of illustrate to you. And let's say that we want to mesh this so that we get at least 3 elements through the thickness. 3 elements is pretty reasonable. So if we want to get 3 elements, then we have to basically split this in 3. 1, 2, 3. Right, so our elements need to be at least this size, right? So the size of the elements that we choose has to be this size right here. Or whatever that size may be, it may be, maybe, 2 millimeters or something like that. Right? The problem is that, when you apply that size, it applies that size to every size of the element. Because remember, elements are generally, they like to be equal matter. So they like to have the same length of the edge on every single side of that element. And so if you choose an element of that size, you're going to end up with a mesh that may look like this. I'm not going to draw all the ones, but you get it. All right, so what this creates kind of an inordinate or kind of an unnecessarily large number of elements just to satisfy that thickness criteria. Number of elements is too damn high for this simple geometry. Now the question is always asked, why don't we just skew the elements, right? So why don't we just make it so that we make them really small in one dimension, but we really kind of stretch it out in the other dimension. There are ways to do that, and so that's not impossible to do. It's just that you kind of at that point you kind of run the risk of kind of intentionally skewing your elements, which can kind of lead to other adverse adverse outcomes for your results as well. Okay. There are some situations where you'd want to do that. I'm not going to say that that's not a terrible decision a lot of the time, but it's usually not one that you're not making unless you really know what you're. Especially when there's a much easier way to kind of deal with these by just kind of switching to shell elements. Okay. So the proper way to deal with this, or kind of the most elegant way to deal with this, is to switch the element types. So instead of trying to kind of force 3-dimensional elements into this very thin geometry, what if we just treat the geometry as if it were 2D and mesh it with appropriate 2D elements? So instead of kind of trying to jam so many hexahedrons in there, what if we just do a very thin plate like this? Okay. Then there's no requirement on the thickness because we're assuming the thickness is essentially infinitesimally small in this case. Okay. So then we're kind of free to mesh it something like this, which is kind of much more reasonable than for you. And this looks a lot more natural in terms of what you would expect for something like this as well. 2D, a 2D flat, element is kind of its natural shape, and so, it should make sense to use an element of that same stature. But you may be thinking, wait a minute, the whole reason we're in this issue is that, we can't put enough elements through the thickness. And so doesn't this violate that exact thing? Because technically this thing has no thickness, and so we just have one element through that thickness. And you're right? And so by eliminating that kind of third dimension there, we are eliminating the thickness. But shell elements are not just traditional 2D elements. They have kind of a little bit extra to them. As a traditional 2D element would only compute, X and Y deformations at each of the nodes, kind of like exactly we did in activity 1. Shell elements are a little bit special because they actually compute extra degrees of freedom at every node of their, So even though they're 2D elements, we're using 2D elements in a 3-dimensional space, in a 3-dimensional application. And so that means we have to compute extra degrees of freedom. Because you're going to still want your results to be in 3 dimensions. So, there are extra degrees of freedom. And so the first one that's computed is, obviously deformation in that 3rd dimension. So deformation in all 3 dimensions. So that means, with this shell element, we can actually get out of plane motion, which is kind of cool. Looks pretty cool when you see it. It's like, you have this piece of paper in your finite element simulation that's kind of doing this, like kind of doing like a gymnastics move or something. Okay, but the other thing that computes that's really unique to shell and beam elements is they compute something called rotations as well. And so rotations also have 3 dimensions, X, Y, and rotations, traditionally in kind of a traditional solid element FEA, only the nodal deformations are computed. Okay. And then based on those nodal deformations and the relative positions of those relative to the elements, then the orientations of those are known. What's different about shell elements is that the orientation or the direction of the shell structure is actually directly computed as part of the solution as well. So when I say rotations, what I mean is the element orientation or the orientation of the element itself is computed. It's very interesting. So, you would directly actually compute that. And if your element kind of distorts, and so if you have one side of your element that's one orientation, the other side that's different, you can actually directly compute that in the shell elements. Whereas in the solid elements, those would be kind of, derived kind of implicitly based on your deformation solution. Okay, and so because of these extra degrees of freedom, it actually gets around that you know, it actually gets around that difficulty of computing things without interior nodes. Those extra degrees of freedom are. All right, any questions on this? Okay, one last thing before we head out for today. And so, you know, when you have a shell structure like this, you know, it's gonna be infinitesimally thin, so there's no actual thickness there. But, you know, the thickness information of the original structure is not lost, right? Because in reality, you know, you're using the shell element to model a three-dimensional structure. So you're not, you know, you're not in Paper Mario or something. So the thickness information is not lost, it's still stored. Because you can make a shell element out of a structure that is 5 millimeters thick. You can also make one out of a structure that's 10 millimeters thick. And of course, you know, those are going to have different behaviors when you run them through a finite element equation. And so because we're, you know, geometrically eliminating this thickness by using the shell elements, we need to factor that into our solution somehow. And so the thickness information is stored not geometrically, but it's instead stored as a material property. And so just like we would for like the Young's modulus, just like we would for the density, you know, those are kind of stored on kind of a nodal element level, right? They're just basically values that are stored within the element. The thickness is stored in exactly the same way. And so when you form, we'll talk about this next time, but when you create a shell element, basically you're going to take your structure and kind of eliminate that thickness, right? You're going to do an operation that's called a mid surface. And so when you do that operation based on that thickness, whatever it was, it remembers that and it stores it as a number that be remembered by the element. And that number, that thickness, is actually incorporated into its modified governing equations that are used to compute the extra degrees of freedom. All right, any final questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for today. So Tuesday, I promise we'll talk about the midterm project, and so, you know, you're gonna hold me to that. I know I promised you today, I apologize, but Tuesday for sure we'll talk. Tuesday, we'll introduce the midterm project. It's gonna be due April 6th, I think, the week after the comp exam. We got about 5 weeks to work on. Okay, so hope you guys have a good weekend. Thanks for coming out today, and I will see you next week. Yes, we are, yeah. So activity 4 and probably activity 5. Yeah. Yeah, so sometimes that can happen. Certain computers, certain geometry. Say no. So in those cases, you just need to. Yeah, it happens sometimes. The thing with meshing is that there's some randomness associated with the example of the node. So sometimes it just fails. You can try so many things, but it doesn't work. Yeah.
Thank you.